Hello, aviation enthusiasts. Welcome back to SMT Academy. The design process of the aircraft engine design. The design process for air-breathing gas turbine engines. In this video, we will explore the various stages involved in designing these engines and highlight the unique aspects of the design process. Before we dive into the details, make sure to subscribe to this channel and activate the notification bell if you haven't already. Designing is different. Let's begin by understanding what makes the design process unique. In this video, we will focus on critical elements that are commonly agreed upon by designers. 1. Identifying the need. The design process is both started by and constrained by an identified need. The need. Gas turbine engines play a crucial role in aircraft performance and must be tailored to specific applications. The customer's requirements for aircraft performance are typically outlined in a request for proposal, RFP. However, the RFP focuses on the final aircraft capabilities rather than the detailed design. The issuance of an RFP marks a critical milestone in a sequence of events that started years earlier, with discussions between the customer and potential suppliers. The competitive nature of the industry and the significant investment involved drive the boundaries of technology and innovation. Selecting the best solution from many possibilities. Designing a gas turbine engine requires careful consideration and systematic methods to identify the best solutions. Iterative process requiring revisiting earlier steps. It is an iterative process, often requiring revisiting earlier steps when assumptions prove to be invalid. Interwoven technical specialties, such as thermodynamics, aerodynamics, and manufacturing processes, are interwoven in the design. Active participation and disciplined communication. Effective communication and collaboration among all involved parties are crucial for finding optimal solutions and avoiding conflicts. Compression flow relationships. Let's now explore 6 important compressible flow relationships that are frequently used by designers and engineers. These relationships provide valuable insights and are easy to apply. They are evaluated at specific points or stations in the flow and are not dependent on the properties of other points or stations. It is important to note that the ratio of specific heats remains constant in these relationships. 1. Total or stagnation temperature. The stagnation temperature, denoted by T sub T, is equal to the static temperature, T, multiplied by 1 plus 1/2 times the ratio of specific heats, gamma minus 1, times the Mach number, m, squared. 2. Total or stagnation pressure. The total pressure represents the pressure the flow would reach if brought isentropically to rest at a stagnation point or in an infinite reservoir. The total pressure, P sub T, is equal to the static pressure, P, multiplied by 1 plus gamma minus 1 over 2, Mach number, m, squared, all raised to the power of gamma over gamma minus 1. 3. Mass flow parameter. The mass flow parameter, based on total pressure, denoted as MFP, combines mass flow per unit area with the perfect gas law, Mach number, speed of sound, and the equations for total temperature and pressure. MFP, or mass flow parameter, is equal to the mass flow rate, m dot, multiplied by the square root of the total temperature, T sub T, all divided by the product of the total pressure, P sub T, and the flow area. Alternatively, it can be expressed as the mass flow rate per unit area multiplied by the square root of the ratio of the specific heat capacity at constant pressure, static pressure mass flow parameter. The mass flow parameter, based on static pressure, denoted as MFP, is derived by combining equations for total and static pressure. The static pressure mass flow parameter, SPMF, can be expressed in two ways. The first way is the mass flow rate, denoted by m dot, multiplied by the square root of the static temperature, T, divided by the product of the static pressure, P, and the flow area, 5. Impulse function, impulse, denoted by I, is equal to the product of pressure, P, and area, A, plus the product of mass flow rate, m dot, and velocity, V. Alternatively, it can be expressed as pressure, P, times area, A, multiplied by, plus the product of mass flow rate, m dot, and velocity, V. Alternatively, it can be expressed as pressure, P, times area, A, multiplied by 1 plus gamma times Mach number, m, squared. 6. Dynamic pressure. Dynamic pressure serves as a reference scale for both inviscid and viscous forces in fluid motion. It plays a significant role in compressible and hypersonic flows and is widely used in estimating pressures and forces on bodies immersed in such flows. It's equal to dynamic pressure, Q, can be expressed in density of the fluid, multiplied by velocity of the fluid, all divided by 2. Dynamic pressure, Q, is also equivalent to gamma, specific heat ratio, multiplied by P, pressure, and m squared, Mach number, all divided by 2. Finally, understanding the design process for air-breathing gas turbine engines is crucial for achieving optimal solutions. By considering the unique aspects of the design process, emphasizing effective communication, and utilizing key compressible flow relationships, designers and engineers can navigate the complexities of engine design successfully. Remember to subscribe to our channel for more informative videos on engineering and technology. Don't forget to like, subscribe, and hit that notification bell for more captivating content. Until next time, keep soaring high with the power of knowledge. Thank you for watching.